Well, hello and welcome again to our journey into algebra and number theory, and we've been looking at applications of some of the ideas in our first section to number theory, and this is the final video in this section. So we were talking about sigma of n and tau of n, and I wanted just to say a little word about perfect numbers which connect in with sigma of n, the sum of the divisors. So perfect numbers really have their history more in numerology than number theory, but they have attracted mathematicians throughout the ages. The number 6 is an example of one of these so-called perfect numbers, and since it's the sum of its own what are called alicot or different factors. So the factor is different from itself. So the factors of 6, of course, are 1, 2, and 3, and if you add these up, you get 6. The next one in the list is 28. If you add up the factors of 28, excluding 28 itself, you get 28 back again. So you add up 1 plus 2 plus 4 plus 7 plus 14. I think they're the factors of 28, and you'll get back to 28. The next one after that turns out to be 496, followed by 8,128, and after that I can't remember what the next one is. It's got quite a few digits in it. So to analyse this, I'm going to define sigma 0 of n to be the sum of the positive alicot factors. In other words, the factors that are not equal to itself. And so if sigma naught of n is n, or equivalently sigma of n is 2n, then we say that n is a perfect number. So sigma 0 of 28 is 28. Now Euclid found a formula for all even perfect numbers, but he wasn't able to prove that every even perfect number arose from this formula. That honour goes back to Euler almost 2,000 years later, and we'll have a look at Euler's proof, and we'll also see what Euclid did. This is also, it's in Euclid, but it's also mentioned in Nicomachus, another Greek writer on Greek arithmetic. Outlined this method all in words as to how to compute these perfect numbers. It also shows you how they might have discovered this formula as well. So it's a very natural thing to write down the powers of 2, 1, 2, 4, 8, 16, so that's a very natural thing to do. And then it was a natural thing to do to start taking partial sums. So you take 1, so the partial sum of 1 is 1. 1 plus 2 is 3, and that gets you a 3 there. 1 plus 2 plus 4, of course, is the same as just adding that one plus that one. That gives you 7, and then 7 and 8 is 15, and then 15 and 16 is 31, and then 63 and 127, and you can keep going along this list. Now, you then multiply by the last number in your head at each stage, so you multiply the 2 times 3, you get 6, well, big deal. You multiply the 7 by 4, you get 28, and now you get a bit more excited because 6 and 28 are the first two even perfect numbers. Well, you multiply 8 by 15 and it doesn't give you an even perfect number, so that's bad. Okay, so we'll forget about that one. You multiply 16 by 31, you get 496, which is, the Greeks knew, was the next even perfect number. You keep going, you multiply 32 by 63, well, you don't get one, unfortunately. And you multiply 64 by 127 and you get 8,128, which again the Greeks knew was an even perfect number. And the trick was to decide whether or not these partial sums were prime. And so in the case of 3 is a prime, 3 2s are 6 gives you an even perfect number. 7's prime, 7 4s are 28 gives you an even perfect number, but 15 is not prime, and that does not produce an even perfect number. 31 is prime, that gives you 1. 63 is not prime. 127 is prime, and that produces an even perfect number. So we can sort of perhaps feel a theorem coming on here. So if the sum that we get, if these partial sums as we move along, we're adding up as we go, if they're prime, then you multiply by the last power of 2 you had in your head, that's the number above, and you get an even perfect number. Now we can and so you can write this down as a formula then, because you can simply add up these powers. If you add up 1 plus 2 plus 2 squared up to 2 to the k minus 1, that's a geometric series, and if you add this up, we've seen before, you just get 2 to the k minus 1. So what we've done here in this little schema here is we've added up the partial sums, which gives me 2 to the k minus 1, and then we multiplied it by the last power of 2, which is 2 to the k minus 1, and provided this number here was prime, this should give me an even perfect number. And there's our little theorem. If n is even, then sigma n is 2n. Now here I claim if and only if n has this shape, with this number 2 to the k minus 1 being prime. Now it's easy to show one way round. If n is given by this, it's an exercise to show that then sigma of n is 2n. And this is not very hard to do, because if this is prime, then I can explicitly write down all the factors of this number n, add them all up, you get a couple of geometric series, and you add them up and you find you get exactly twice what you started with, so you get 2n. That's a nice exercise for you to do. The converse, which the Greeks couldn't do but Euler could, is somewhat more clever, and it's a bit harder, and here's Euler's proof. So we begin by suppose sigma n is 2n. Now here's a little thing in little trick in number theory. If you've got a number n and you know nothing about it whatsoever, what can you do with it? You've got to do something with it. You can't just leave it as n. One thing you can do is to try and say, well, if this n is even, then I can factor out 2 as often as I can until I'm left with an odd number. So that's a useful little trick, sometimes gets you somewhere in number theory, to take a number n and write it as a power of 2 times an odd number. Now of course k could be 1. If this number n is odd, then k is 1, so you just get n equals m, and that's okay. But if not, you can factor out powers of 2. So what I need to do now is, comparing that with our formula, we need to show that this m, this odd number we've got here, is in fact 2 to the k minus 1, and that m is in fact prime. Now we were given that we know that sigma n is 2n. So sigma n, we can work from here. Sigma's multiplicative, so it's sigma of this one times sigma of m. And we know how to work out sigma of 2 to the k minus 1. We saw up here, that's just 2 to the k minus 1 times sigma of m. And I'm going to split this up now into the sum of the Alicot factors plus the factor m itself. Now if you take and this equals 2n by assumption, so sigma n is equal to 2n. And n of course is 2 to the k minus 1 times m, so I can do that. Now all I do now is I'm going to expand out this side, and I'm going to get a 2 to the k times an m, which I can cancel with this term. And then I just rearrange and refactor a little bit, and I get sigma 0 of m times this thing. And I'm going to get a minus m here when I expand, which I take onto the other side. Now, we just enjoy that equation for a moment, and that means that, well, firstly, we note that if I want to try and prove that this sigma 0 of m is 1, and that will do two things. It'll give me m is in fact 2 to the k minus 1, which is what I want. And if sigma 0 of m is 1, then that means this m has to be prime, because it's only got one factor, which is 1. So let me suppose it's not 1. Then m has Alicot factors then. This m has factors at least 1. Sigma 0 of m must be a factor, and this is going to be a factor. And so I can add up these three Alicot factors and say, well, that means sigma 0 of m has to be at least the sum of its three Alicot factors, which is this. And this, of course, is clearly impossible, because this says sigma 0 of m is strictly bigger than sigma 0 of m, which is impossible. That means sigma 0 of m had to be 1. which tells me m is precisely 2 to the k minus 1, and it also tells me the only Ellicott factor of m is 1, and therefore m has to be a prime. And that was Euler's very clever proof of this result. So if you put k as 1 and 3 in, for example, into the formula, you get 6 and 28 respectively. You can check that as a little tutorial exercise to show that if this number is prime, then k must itself be a prime. But the converse is false, unfortunately. So if this number is prime, then k itself must be a prime. So if you're looking for primes of this shape, you need to have k itself being a prime. So for example, if k is 5, we get 496, which is a perfect number. Since 2 to the 5th minus 1 equals 31 is prime. If I put k to be 11, however, 11 is prime, but 2 to the 11 minus 1 is 2047, and that factors. It's not prime. It's 89b31. So it does not give a perfect number. Only relatively small number of these perfect numbers are known. It's not known if there are infinitely many of them. These are unsolved problems. No odd perfect number is known, so we only know even perfect numbers. It's been conjectured that none exist. That's another unsolved problem. Are there any odd perfect numbers? The answer is we just don't know at this stage. None have been found by using computer searches. Clearly, the key to finding perfect numbers then is to find primes of this form, 2 to the k minus 1. And you probably know that primes of this form are called Mercer Primes, named after Marin Mersenne, who first talked about these things and became interested in these. And they are or were used in coding. Now, I'm very out of date here. I haven't looked this up for quite a long time. Here are some large ones. There's 2 to the 756,839 minus 1. That was discovered in 1992, and I've got a whole list of these ones here. The latest one, well, this is not true anymore because lots discovered since then, but this one was discovered in 1998. You might like to Google Mercer Primes and you'll find out the most recent one. They tend to discover these every year or so. In fact, the biggest known prime is a Mercer prime. That wasn't always the case, but I believe it is at this point in time. Final comment on amicable and sociable numbers. Again, of interest historically are the so-called amicable numbers. So two numbers n and m are amicable if sigma 0 of m gives you n and sigma 0 of n is m. And the smallest examples are the famous 220 and 284. These numbers actually are mentioned in the Old Testament, which is interesting. There's a bit of a sort of numerology in the Old Testament, and these two numbers appear there, I think in the book of Genesis. In other words, if you add up all the Ellicott factors of this, you get 248, and if you add up all the Ellicott factors of 248, you get 220. Formulae generating amicable numbers are known, but there is no known formula which gives all amicable numbers, and nor is it known how many there are. Here's some other examples, 1184 and 1210, these are amicable, these two numbers are amicable, and there's two larger numbers that are amicable. The obvious generalization of this is to find a sequence of numbers n1 up to nr such that sigma 0 of n1 gives you n2, sigma 0 of n2 gives you n3, and finally sigma n0 of nr gets you back to n1 again. So you get a sort of cycle of numbers where the sum of the Ellicott divisors of each one leads to the next one all the way around in a circle. And an example of a circle of 5 sociable numbers, 12,496, 14,288, and so on. So sigma naught of that gives you this one, sigma naught of that gives you this one, sigma naught of that gives you this one, and sigma naught of that gives you this one, and finally sigma naught of this one gets you back to home again. So that's the end of this little section, and the next series of videos will be on our third section in this journey into algebra and number theory.